We're going to learn how to use the integrating factor method to solve first order differential equations. I'll start with a motivating example to kind of show you how the technique works. Then we will do the more general case and I will explain how to find the integrating factor in general, and we'll finish with an example that ties it all together quite nicely, and I'll show you all of the details here, including why we're allowed to drop the moduluses and things like that if you've seen this before. So I hope that's going to be useful. If you do like the video, please click like below and subscribe to the channel if you want to stay updated with my latest videos. Don't forget there's also the Mathsaurus website and the Amazon store with loads of other interesting stuff there. I've given the website a big overhaul in the last few days, so do check it out if you haven't looked at it recently. So you want to solve a differential equation that has the form dy by dx plus some function of x that I'll call p here multiplied by y equals some other function of x. Now of course y here is also a function of x, but I'm not going to write that out every time here, and of course you could also think of dy by dx is also a function of x, but we don't tend to write that every time. To begin with, let's just notice one thing, which is that if f of x equals 0, then this is just a separable equation. Okay, so if I have dy by dx plus p of x times y equals 0, then we would just have dy by dx equals minus p of x times y, and you'll need to know how to solve separable equations to do integrating factors here, because so now I want to write this as 1 over y dy integrated is the integral of minus p of x dx, and you can solve this equation, right? Just get log mod y equals the integral of minus p of x dx, and we hope that we can integrate the right hand side here, so I just get mod y as e to this integral. Okay, so in general here we're going to be thinking about the case where f of x is not 0, so we're doing something new. So let's start with an example to give you a flavour of how this method works. So if we have dy by dx plus 2 over x times y equals x cubed, what we're going to do is multiply by another function to turn this into an easier differential equation. It looks like we're making it more complicated at first perhaps, but you'll learn how to choose this function of x that we'll multiply by to make this work. In the first one, I'm just going to tell you that it's x squared, so if I multiply this whole differential equation by x squared, I get x squared dy by dx plus 2xy is equal to x to the 5. Now, the nice thing about this choice is it makes the left-hand side an exact derivative of a product. And in particular, it's the product of x squared times y, that's the function I multiplied by, and y differentiated, right? Because if I differentiate this by the product rule, I leave the x squared alone and differentiate the y, and then I add it to what I get when I differentiate the x squared, which is 2x, and leave the y alone, right? So that's exactly the left-hand side here, right? So actually I can write this differential equation as d by dx of x squared y is equal to x to the 5. Then, integrating both sides, we just get x squared y is the integral of x to the 5 dx, or x squared y is 1/6 x to the 6th plus a constant. Okay, so we hope that we can integrate whatever function we end up with on the right hand side. Now I divide through by the x squared and I get y equals 1/6 x to the 4 plus c divided by x squared. So my arbitrary constant here is perhaps in a slightly different position to usual. It's I'm getting an arbitrary function divided by c over x squared here. So it's still an arbitrary constant, but it's not just a plus c like when we do ordinary integration. Okay, so so the question is, how do we find the function that we want to multiply by to make this work? So let's have a go at another example. Okay, so we'll do dy by dx plus 3 times y is equal to x, right? So the aim here is that we're going to multiply by some function, and I'm going to call this function mu, and actually, mu of x is what we're going to be calling the integrating factor. Okay, so I'm going to have mu of x times dy by dx plus 3y times mu of x equals x times mu of x. And I want to make it so that the left-hand side is just d by dx of mu of x times y. Okay, so d by dx of mu of x times y is mu of x times dy by dx plus d mu by dx multiplied by y. Okay, so you can see we've already got this term matching up here. So all I've got to do is choose this term to equal this term, and we'll be done. Okay, so I want to do d mu by dx times y equals 3y times mu of x. Okay, so and let me drop the emphasis on x here. So I can divide both sides here by y, and we just get d mu by dx equals 3 mu. Well, this is just a separable differential equation here, right? I can write this as 1 over mu d mu integrated equals the integral of 3 dx, and then I get that log of modulus of mu is equal to 3x plus a constant. And there's a little subtlety here, which is we are choosing a function to turn the left-hand side into an exact derivative. So there are lots of choices here, actually. In fact, I could take any value of this constant c and it would work. But we want to keep the method as simple as possible, so we're just going to choose this c to be 0. Okay, and that will be an example that works as an integrating factor. Right? And similarly here, when I do modulus of mu equals e to the 3x, right? Well, again, I just want any function mu that satisfies this equation, right? So I could take here mu equals plus or minus e to the 3x. Either of them would work. I'm just going to choose the plus and make the integrating factor as simple as possible here, right? So our integrating factor is going to be mu equals e to the 3x, right? So let's go back to the equation we were looking at here, and we'll multiply by our integrating factor. So I'm going to get e to the 3x times dy by dx plus 3e to the 3x times y equals x times e to the 3x. And then the left-hand side will necessarily, because we've chosen it for exactly this reason, be d by dx of y times e to the 3x. And you can check that if you apply the product rule, you get exactly these two terms. Okay, so I get x times e to the 3x. So the next step, I just have to integrate both sides, and then again we hope that what we've ended up with here is something that we can integrate, and of course we can here, right? I mean, let's just do this as a little side problem, I suppose. I want to integrate x times e to the 3x dx, so I can apply integration by parts with u equals x and v primed equals e to the 3x. So u primed is 1 and v is 1/3 e to the 3x, or however you want to write this down, right? So this integral is u times v, so that's 1/3 x e to the 3x minus the integral of 1/3 e to the 3x dx. So this is 1/3 x e to the 3x minus 1/9 e to the 3x plus a constant. Okay, so actually going back to the original problem here, then I've got y e to the 3x is equal to 1/3 x e to the 3x minus 1/9 e to the 3x plus a constant. So dividing through by the e to the 3x here, we get y equals 1/3 x minus 1/9 plus c times e to the minus 3x, and that's the solution to that differential equation. Okay, so this method is quite nice. Okay, so what I want to look at now is the general case. Okay, so we will go back to that differential equation, dy by dx plus p of x times y equals f of x. And again, our aim is just to multiply by some integrating factor mu of x to make the left-hand side an exact product rule derivative. Okay, so we're going to do mu of x times dy by dx plus p of x mu of x times y is equal to f of x times mu of x. And again, if you think about what you get when you differentiate mu of x times y, we get mu of x dy by dx plus y times d mu by dx, exactly as before. So again, as before, these two terms match up, and I just want to make this term equal to this term. Okay, so we're going to have p of x mu of x times y equals y times d mu by dx, and again the y's cancel here, so I'm just looking to solve this separable differential equation, d mu by dx equals p of x times mu of x. I'll just write that as mu again, so I get 1 over mu d mu integrated equals the integral of p of x dx. And again, log mod mu equals the integral of p of x dx. So again, we get the modulus of mu equals e to the integral of p of x dx. And again, for the same reasons before, okay, I can take, mu equals plus or minus here, but we can take either of those, so why not just choose the positive one? And that is our general formula for an integrating factor here. Okay, so the integrating factor that we multiply by in general is going to be mu of x is e to the integral p of x dx, right? And in fact, if we go back to the very first example where I just picked x squared out of the hat here, right? If I try to apply that to this one, I would have to do, so I want to do integral e to the integral of the p of x in this one is 2 over x dx, and so I'm going to get e to the 2 log mod x here, which is e to the log of mod x squared, which is just mod x squared. And I'm going to say something more about this later on. For this case, we can notice that actually the modulus of x squared is just x squared. In fact, in general, you can ignore these modulus signs when you get them at this stage and take this to be the integrating factor. But I'm going to show you that in a bit more detail in the final example that we go through. Okay, so let's do one more example of this method. So we're going to have cos x this time times dy by dx plus sin x times y, and I want to solve that as equal to cos squared of x. Okay, and actually we'll also put a boundary condition on this one, so we'll say that this is subject to y of 0 equals 2. Okay, all I mean here is that when x equals 0, y equals 2, and that will allow us to make sure we don't have an arbitrary constant in the answer at the end. Okay, so the integrating factor here is going to be e to the integral of, well, okay, actually before I do this, I need to get my differential equation in the right form. Okay, I need it to be dy by dx plus a function of x times y. So I'm going to divide through by cos x here. So I get dy by dx plus tan x times y equals cos x. And then my integrating factor is going to be e to the integral of the tan x here, dx. And you might know what the integral of tan x is. If not, we will think of it as integral of sine x over cos x. In fact, maybe I'll write it as minus sine x over cos x dx, right? Because that's then in the form, exactly in the form of the integral of f prime of x over f of x, and we know that this gives us log mod fx plus c, right? So this integral here is just log of mod of cos x plus c, and I've got a minus out the front because cos differentiates to minus sine. So this is log of 1 over cos x, which is log of mod of sec x then, plus c. Okay, and again, for the same reason as before, we're just going to choose c to be equal to 0 in this example, right? So I'm going to get e to the modulus of sec x, log of sec x, sorry. E to them, okay? So actually my integrating factor here then, I'm going to say is mod of sec x. Right? Now, okay, so why can I just get rid of the modulus sign here and say the integrating factor is sec x? Well, if we go back to the way we derive the integrating factor, if you think about it, all we're trying to do is find a function such that d by dx of mu, or I could just say d mu by dx here, right, is equal to mu times tan of x, right? If you go back to the derivation here, when you match up these two red terms, I'm trying to find a function such that d mu by dx is equal to p of x times mu here, right? So, okay, firstly, actually one thing you can just notice is that d by dx of sec x is sec x tan x, right? So without any further thought, just sec x is a valid integrating factor here. But if we also want to try and apply this by the usual separable differential equation method, I'm going to get the integral of 1 over mu d mu is the integral of tan x dx, right? So I get log mod mu is log mod sec x, and again I've got plus some arbitrary constant. Perhaps you can put an arbitrary constant on both sides if you want, or just on one side. But the point is, all I want is to choose a function that satisfies this equation, again, for any value of c that I can choose. So I can just get rid of the c here and choose c equals 0, and I can just notice that mu equals sec x definitely satisfies this equation, right? So if you like, the implication arrow is perhaps in the opposite direction to what you're thinking about if you're unsure about why I can just take off the sec x here, and it's because of this way we usually just write down the result of this logic for integrating factors rather than working through it every time. Okay, so I'm just looking for any function that satisfies this equation, so I can quite happily just not worry about that and use take our integrating factor as mu of x equals sec x, right? I mean, the fact that it works when we multiply through by it is in some ways argument enough, because we're just trying to find a way of undoing this logic. But that's somehow satisfying to know we can see our way through that logic. Okay, so what do? We multiply our differential equation by the integrating factor. So I get sec x times dy by dx plus, now, okay, so this tan x, let's write it as sine x over cos x again. And if I multiply by another 1 over cos x, that'll give me sine x over cos squared x times y. Cos x times sec x is cos x times 1 over cos x, which is just 1. And again, we know now that d by dx of y times sec x, well, that's exactly what we've got here. Sec x times dy by dx plus y times the derivative of sec x. Okay, and if you are really still worried about my modulus or something, you can just check here. Well, the derivative of sec x is d by dx of 1 over cos x, so that's minus 1 over cos squared x times the derivative of cosine x, which is minus sine x, so I do get exactly what I want here. So that's equal to 1, so I can just integrate through here, y sec x equals x plus c, and so we've got y equals x times cos x plus c times cos x, and in this question I said we'd have a boundary condition here that when x equals 0, y equals 2, okay, so I can just plug that in and I'll get 2 equals 0 times cosine of 0, so that's just 0, plus c times cosine of 0, cos of 0 is 1, so I've just got c equals 2, and my final solution here is y equals x times cosine of x plus 2 cosine x, which if you like perhaps I could write that as x plus 2 times cosine of x, and then we're done.